In this video, we are going to go through tutorials and walkthroughs for solving various types of momentum problems. We'll do momentum impulse, bouncing, inelastic collisions, and explosions. For all four types of problems, there are only 4 steps. You start by drawing a picture with labels that takes all the information from your problem and puts it into one diagram. Then you organize your information with the bar chart, which I will always provide you, and then you substitute equations and simplify to get your final expression before you substitute and evaluate to get the final result. We are starting with a momentum impulse problem. A 1 kilogram soccer ball at rest is kicked with a force of 20 newtons for 0.1 seconds. How fast is it going after the kick? So you start with step 1, which is draw a picture with labels. For all of these, we're going to have a before and an after. So the before, you have your soccer ball, and you have a foot getting ready to kick it. For labels, we know that the initial velocity is 0 meters per second because it says it is at rest. After, now we have our ball is moving because our foot has kicked it. We're looking for the velocity afterwards because we don't know that. The mass of the ball is 1 kilogram. The force is 20 newtons, and the time is 0.1 seconds. So now we've drawn our pictures with all the labels organizing the information from our question. Now we fill in the bar chart. We know the momentum before, in the before picture, is 0 because our velocity is 0. So we know it has no momentum when it starts. After it's been kicked, we know that it has some amount of positive momentum because it is moving to the right. In order to go from 0 momentum to some positive momentum, you must have some positive impulse, because impulse is how you change momentum. So we've done step 1, draw our picture with labels. Step 2, organize our information on our bar chart. For step 3, we simplify and substitute our equations. So our initial momentum is 0. We know that impulse is going to give us force times time. And the final momentum is going to be mass times the final velocity. So then we can rewrite this to say that force times time is equal to mass times the final velocity. Then with that, we can do step 4, which is substitute and evaluate. So our force is 20 newtons. Our time is 0.1 seconds. Our mass is 1 kilogram. And we're trying to find the final velocity. So 20 times 0.1 is 2, is equal to 1 kilogram times the final velocity, which is just the final velocity. So our velocity final is equal to 2 meters per second, and box your answer. Next, we'll be doing a bouncing problem. A 0.1 kilogram ball is traveling at 5 meters per second, hits a wall and bounces back at 3 meters per second. If it is in contact with the wall for 0.2 seconds, how much force did the wall feel? We start by drawing a picture. Here's the wall. Before the ball is going towards the wall with a velocity of 5 meters per second. After the ball is moving away from the wall with a velocity of -3 meters per second. It is negative because now the ball is moving to the left, and with momentum, when you have anything that is a vector, negative just means the opposite direction than what we consider positive. So negative means it is moving down or to the left. We know the mass is 0.01 kilograms, and the time of impact is 0.2 seconds. So there is our picture with all of our information labeled. Step 2, we fill in our bar chart. So it starts with some positive momentum. We don't know exactly how much, but we know it's some positive momentum. It ends with some negative momentum. We don't know exactly how much, but we know it's negative because the velocity is negative. For impulse, in order to go from some amount of positive momentum to some amount of negative momentum, our impulse has to be negative and bigger than either of the other two. So if this is positive 2 and this is negative 2, in order to go from positive 2 to negative 2, we need to have an impulse of negative 4. So now we've filled out our bar chart. We do step 3, which is substitute and simplify equations. So our initial momentum is going to be mass times the initial velocity. Impulse is force times time. And our final momentum is going to be mass times the final velocity. So then we rewrite that. Mass times the initial velocity plus force times time is equal to mass times final velocity. Then we substitute and evaluate. 0.01 kilograms times 5 meters per second plus force times time is equal to 0.01 kilograms times negative 3 meters per second. So then we evaluate. I'm going to give ourselves a little bit more room. So we have 0.05 plus force times 0.2 seconds is equal to negative 0.03. Subtract from both sides. We get 0.2 times force is equal to negative 0.08. Divide both sides by 0.2. And we end up the force is equal to negative 0.4 newtons, and box your answer. So there is the final answer and solution for a bouncing problem. Our next problem with momentum is going to be an inelastic collision. A train car with a mass of 500 kilograms traveling at 7 meters per second hits and sticks to a train car with a mass of 200 kilograms. How fast do they both travel after the collision? Step 1, draw a picture. Before, we have one train car with a mass of 200 kilograms. We have another train car with a mass of 500 kilograms. And it has a velocity of 7 meters per second. After, now the two train cars are stuck together. One has a mass of 500 kilograms, the other one still has a mass of 200 kilograms, but they're moving this way, and their final velocity, we don't know that yet. So, step 1 complete. Step 2, fill in our bar chart. Initially, we're going to call this one A and this one B. So car A has some positive momentum. Car B has no momentum because it is at rest. After, in order to make the initial momentum is equal to the final momentum be true, the final momentum of both of them together has to equal the initial momentum of A by itself. So now we can substitute and simplify our equations. So the momentum of A is the mass of A times the velocity of A. The momentum of car B is 0. And then both together, and here's the key, it's their combined mass. Mass A plus mass of B times the final velocity. So now we rewrite this so that we have mass of A times the velocity of A is equal to the combined mass of A and B, mass A plus mass B, times the final velocity. Now we substitute and evaluate. Mass A is 500 kilograms with a velocity of 7 meters per second. That has to be equal to their combined masses, which is 700 kilograms, times final velocity. So 3,500 is equal to 700 times final velocity. Divide both sides by 700. Zeros cancel out. You can factor out a 7. That will become 1. That will become 5. So the final velocity is equal to 5 meters per second. And box your answer. The last momentum problem we're going to look at today is an explosion. Sandy, with a mass of 60 kilograms, and Alex, with a mass of 30 kilograms, stand on frictionless ice and push away from one another. If Sandy moves backwards with a velocity of 4 meters per second, how fast does Alex move? So we start with our pictures. Before, and I draw my people as rectangles because rectangles are easier to draw. Here is Sandy, right next to Alex. So the mass of Sandy is 60 kilograms, and the mass of Alex is 30 kilograms, and their velocity at the beginning is 0 meters per second. After they've pushed away from each other, so we have Sandy going backwards, and we have Alex going forwards. The velocity of Sandy afterwards is negative 4 meters per second. The velocity of Alex is unknown. Masses are the same. So then we can use our bar chart. Before, when they're together, that's what this means, momentum of Sandy and Alex. Their velocity is 0, so that means their momentum is 0. The momentum of Sandy afterwards is some negative value. We don't know exactly how much, but we know it has to be some negative value because he is moving to the left. So in order to find the momentum of Alex, in order for this equality to be true, their initial momentum has to equal their combined momentum after the push. Alex has to have the same amount of positive momentum as Sandy has negative momentum. So that's our bar chart. Now we can substitute and simplify our equations. We know their initial momentum is 0. The momentum of Sandy is going to be mass of Sandy times velocity of Sandy. And the momentum of Alex is going to be the mass of Alex times the velocity of Alex. So we can rewrite that as 0 is equal to mass of Sandy, velocity of Sandy, plus mass of Alex, velocity of Alex. So we've substituted and simplified our equations. Step 4, substitute and evaluate. 0 is equal to 60 kilograms times negative 4 meters per second plus 30 kilograms times Alex's velocity. 0 is equal to negative 240 plus 30 times the velocity of Alex. Add 240 to both sides. We get 30 times the velocity of Alex is equal to 240. Divide both sides by 30. And we get the velocity of Alex is equal to 8 meters per second, and box your answer. Now, since we know their momentums have to be equal, it should make sense that if Sandy has twice the mass of Alex, that he will have half the velocity. 60 kilograms times 4 meters per second is the same as 30 kilograms times 8 meters per second. And that is the end of our tutorials for solving momentum problems.